Hello everybody. In this lecture I'm going to go through ionization energy. So I started the lecture with ionization, and after that one we will move to electron affinity, and we will end the chapter with metallic character. What's ionization energy? Ionization energy is the energy that we need to spend to take one electron. From any species that's in a gas phase. It has to be in a gas phase. Okay, you spend energy to take electron from it, and that's gonna be the ionization energy. So that means energy will be added to the reactant. So I'm gonna add here energy. Energy plus one species in a gas phase, we will get ion plus one electron. This is the energy that we spend to take first electron. So I'm going to say this is going to be the first electron, because it's the first electron, it will be the first ionization energy. If you want to take the second electron, you will be taking electron from a species that is already missing one electron, and it has extra proton. So there is higher force on the remaining electron. Because there is higher force, we have to spend more energy to take this electron. So let's call this one E1, and this is this one is going to be E2. So E2 always going to be bigger than E1. Again, because this one is already missing electron. So it has less will to give the second electron. Now, the question is, why do we need to have the species in a gas phase? Because we want to know, when we are taking one electron, how much energy we are spending. We don't want to deal with, say, for example, melting, vaporization, or put it in this way that we don't want to deal with any phase change. I don't want to spend energy to, for example, turn the solid to liquid or liquid to gas. I don't want to do that one. And I want to be sure that the only factor I will be dealing with is taking electron from neutral compound. And that's the reason I said I needed to be in a gas phase. Okay. So as I said, we're going to spend energy to remove one electron from a species in a gas phase, and we call it ionization energy. Ionization energy always will be a positive number, because we're spending energy, we're giving energy to the species. Okay. First, ionization energy is the energy that you need to spend to take the first electron. Look to sodium. First ionization energy is around 500 kilojoule per mole. Why do we call it kilojoule per mole? Why do we use mole? If you want to calculate energy of taking one electron, just one electron, you have to start with one sodium. And then you get one sodium ion plus one electron. Energy is going to be so small that it doesn't matter which device you are using, error that you will have, it will be some, it can be close actually to energy that you calculate. And in order actually to get better result, we try to calculate energy of 1 mole, because we are dealing with big number of atoms or electrons. In this case, the energy will be big enough, way bigger than the error of the device, so you can trust that number much better than 1 electron. It doesn't mean that there is no way to calculate, energy of 1 electron, removing 1 electron. You can do it. That's fine, but we prefer to go with 1 mole. So this number means if you start with 1 mole sodium, you will get 1 mole sodium ion and 1 mole electron. So 1 mole electron. Now look to the second ionization energy. When you take the second electron from sodium, you'll see a huge jump. It's 10 times of the first one. Okay, so the second one is 10 times of the first one. Now what's the problem here? I said true, if you take 1 electron from a species that's the already missing electron, you will spend more energy. You will be spending more energy. But why is so significant? Why this one is so huge? You know, the gap between them is so huge. And if you write electron configuration of sodium and you compare it with sodium ion, you will find your answer there. So let's go with sodium. Sodium, okay, it has 11 electron and 11 protons. So we go with 1s2, 2s2, 2p6, 3s1. Okay. So here is sodium, nucleus of sodium. We have the layers, and 1 and 2 and n equal 3. N1 we have 2 electrons, and 2 we have 2 plus 6, 8, and N3 we have only 1 electron. We are targeting the last electron. So here is the last electron. This is the distance of, this is the radius of neutral sodium. We say force is equal to K, Q1, Q2 divided by square of R. Now let's call this one 1. And now compare it with the sodium cation. It will be 1s2, 2s2, 2p6, and 3s, 1 minus 1, 0. So this one, it will be gone. That means we have the nucleus of sodium plus 1 and 1, 2 electrons, and N2 we have 2 plus 6, 8. So we are taking electron from this layer. And let's call this one R of sodium cation. Force, it will be K, Q1, Q2 divided by square of R. I'm going to call this one 1, and I will call this one 2. Okay, to represent the sodium cation. R2, or R of sodium cation, smaller than R1, or the sodium metal. So F1 is going to be smaller than F2. Okay, meaning of this one, F1 will be smaller than F2. Okay, F1 smaller than F2. That means there is less force on the last electron. If there is less force, then you're going to spend less energy. Okay, because this is way far from nucleus, because it's way far from nucleus, it's easier to take it. But here, the distance is less. This electron is under control of the nucleus with extra actual positive charge. So we have to fight with the nucleus to take last electron. And that's the reason we are spending more energy. More energy. Okay. So yes, we are spending more energy. But why is such a, gap? Why is 10 times, almost 10 times? Look to the first electron. First electron that we took it from outer shell. Okay, we took it from valence electrons. But here we took the electron from core electron. Okay. If you take the first electron, it's going to be from valence. But when you take the second electron, you have to move to inner layer because the outer is gone. So you will be taking it from inner. And because you are taking it from inner layer, which is closer to the nucleus, you will see huge jump with the ionization energy. So anytime you see there is a huge jump between the, ionization energies, that means you switch from valence electrons to core electrons. And actually, wherever we find that gap, we can calculate how many valence electrons we have. And I'm going to show you that one. Okay, so let's assume for one element X, first ionization energy is equal to, let's say, 400 kilojoule per mole. Second ionization energy is 900 kilojoule per mole. And the third ionization energy, this time it says, let's say, okay. We can go with that one. And then fourth ionization energy, I go with, let's say, I'm just making this number. Okay. So, and I'm gonna say, you know what, like I see there is a huge jump. Okay. Let me make it, you know, make this one 16 here, sorry, 16. Make it 1600. So we have 400, 900, 1600, and this one is 8,000. 8,000. So I'm gonna say the gap is here. Gap is between the third and the fourth one. So I'm gonna separate the fourth one from the rest, and I'm gonna see X is an element that from group 3, or it has 3 valence electrons. Okay. How do I know I have a 3? I see here 400. I see it increases, is logical because we are taking from a positive electron from positive species. The third one is going to be bigger than the second and way bigger than the first one because you're taking electron from a species that now is a +2, and that one is going to fight with you. But the third one, like the fourth one, when we took it, we saw a huge jump. It's way bigger than the first one, the third one, and that means, you know, you touch the core electrons. Now that I touch the core electrons, I'm going to say, you know, I will stop here. 1, 2, 3. I have 3 valence electrons, or this element is element from group 3. So that's the way we find, you know, we find the number of valence electrons. So simply find the gap across the one that it has the highest, you know, kind of like the one that, you know, like it shows huge gap in ionization energy. And now go back and start counting how many ionization energies you have. And per each ionization energy, give 1 valence electrons. 1, 2, 3 valence electrons. Okay. Now, trend for ionization energy. Trend for ionization energy is opposite of size. Okay. So when the size is getting bigger, ionization energy it will be smaller. Okay. So the trend we say is going to be opposite. Here, you say size to the right side of the periodic table decreases, down in one group decreases. Ionization energy to the right side of periodic table. If size is getting smaller, ionization energy, it will go up. When size is getting bigger, ionization energy decreases. So, for example, sodium, it has a smaller size than potassium. Okay. So we say size of potassium bigger than sodium. Okay. This is the trend for size. And when you compare the ionization energy of sodium is going to be higher than ionization of potassium. Okay. Let's talk about, you know, the size. We said size. Potassium is, my bad, why I am writing Potassium, not krypton. Okay, so potassium is going to be argon 4s1, so the highest n is equal to 4. Sodium is neon 3s1, the highest n is equal to 3. You want to compare them based on size, you go with the n. N4 versus N3. N4 it will have bigger size than N3. So K it will have bigger size than sodium. When it comes to ionization energy, N3 will have higher ionization energy than N4. So sodium, because it's smaller, its electron are closer to the nucleus, so it will have higher ionization energy than potassium. Okay. That's the trend when it comes to ionization energy. How about here? How about let's say silicon versus chlorine. Silicon belongs to N equal 3, chlorine N3. To the right side of the periodic table, okay, size is getting smaller. This one has 14 protons, that one is 17. Both of them belong to N equal 3. I can't judge based on N, I go with number of protons. The one that has more protons, it will be bigger. So protons 14, protons here 17. So we're going to say silicon, it will be bigger than chlorine. This is a trend for size. It has less protons, so it will apply less force on outer electron. That means it will be bigger. When it comes to ionization energy, so we said N equal 3, N equal 3. Protons equal to 14, this one equal to 17. The one that has more proton or smaller, it will apply more force on outer electron. So ionization energy is going to be higher. The ionization energy of chlorine will be higher than ionization energy of silicon. So trend opposite of size. Here, size to the right side decreases, down and increases. Ionization energy to the right side goes up, and here goes down. Okay. So I told you that to the right side ionization energy goes up, down in one group, decreases. And next thing that you need to know it is when you're dealing with full orbitals or half occupied, either half or full occupied orbitals, you will have actually kind of weird or like kind of like unexpected trend. Example of here, oxygen versus nitrogen. Oxygen 1s2, 2s2, 2p4. Nitrogen 1s2, 2s2, 2p3. Let's draw last orbital. We have 4 electrons, and for nitrogen we have 3 electrons. Let's take 1 electron from each. We go oxygen. If we take 1 electron from it, we want to generate O plus. So it will be 1s2, 2s2, 2p. We have 4 minus 1, it will be 3. So the last orbital, it will have 3 electrons. And nitrogen, if you take 1 electron from it, it will be 1s2, 2s2, 2p, 3 minus 1, 2. Okay. Trend for size, it says to the right side of the periodic table, to the right side, size decreases. You will see nitrogen and then oxygen. Oxygen is on the right side of nitrogen. So size of oxygen is going to be smaller or less than nitrogen. So the expected trend for ionization should be opposite of the size, and you should expect that oxygen will have higher higher ionization energy than nitrogen. Yes, this is true. This is true until you start, digging inside the last orbital, and you will see something, that is giving you energy or paying off some of the energy that we spent to take the electron. So let's look to the last orbital. Last orbital is not either full or half occupied. This one is half occupied for nitrogen. So there is a symmetry. There is a symmetry. All these orbitals are half occupied. And we said in quantum mechanics, this is going to be really stable orbital. When we take 1 electron from oxygen, we're going to take this electron, the one that is pointing down, and we'll turn it to like nitrogen. So O plus, it will be like nitrogen. Like nitrogen. And when you take 1 electron from O plus, you will get half occupied orbital. And this one is a stable orbital. So it's going to pay off some of the energy. It will pay off some of the energy then that O supposed to take to lose 1 electron. And because of this stabilization energy, ionization energy of O, it will be less than nitrogen. It's not really less than nitrogen. If you don't count this one, if you don't count it, ionization energy of O will be higher than nitrogen. But if you consider the stabilization energy that you get, and you add this one to whatever you spend at the beginning to take electron from oxygen, you will see you spend more energy for nitrogen than oxygen. Because you are taking electron, okay, when it comes to nitrogen, you are taking electron from half occupied orbital, is very stable orbital, while oxygen, you take it from one that is not stable, it's not half occupied, it's generating half occupied orbital. So here is the problem. Taking electron from half full filled or half occupied orbital or full occupied orbital, it will be harder. It will be harder. Okay. Because you will be fighting with the stabilization energy or the symmetry that you have. If you want to take electron from this system, you're going to ruin the symmetry. So you have to spend more energy. If you take electron from this system, you will get something like this, which has symmetry. It will be stable. So symmetry of the last orbital that you will be dealing with, it will be important. If you take 1 electron and you get half occupied orbital or full occupied orbital after taking electron, you will get some stabilization. So the total ionization energy will be less. Okay, will be less. So I'm going to say because of the stabilization we get, because of the half occupied orbital we get, ionization energy of O in reality is less than ionization energy of nitrogen. This is expected. And this is real one. So we had this trend for, ionization, for size. We said as we go to the right side of periodic table, size decreases. Ionization energy, it will go up. Okay, ionization energy, it will go up. Size decreases. And when you go down in one group, size goes up, while ionization energy, it will go down. Okay. Here the trend for different elements. Start with hydrogen. Hydrogen belongs to N1, helium N1. Okay. To the right side of periodic table, size decreases, ionization energy goes up. So from hydrogen to the right side, which is going to be helium, size decreases. That means ionization energy is going to be it will be higher. And then I jump to N2. I added one layer. Because I added one layer, size got bigger, ionization energy will be smaller. And as you see, there is a huge drop with the ionization energy. And as we move to the right side of periodic table, ionization energy is going to be bigger because the size is getting small, shrinking. Okay, I see some deviation, and let's see a reason behind them. This one is belong to lithium, and then you have beryllium and boron. This is carbon, nitrogen, oxygen, and fluorine. So this one is lithium, here it will be boron, and that one is beryllium. Let's talk about this too. I already talked about nitrogen versus oxygen, but this too. You have 1s2, 2s2. Last orbital is the s orbital, and you have 2 electrons in it. Sorry, this one is 5. That one is 4. I meant 2 by valence electrons, not the atomic number. Okay, so it will be 1s2, 2s2, and 2p1. So last orbital is a p orbital, not s, and you have 1 electron in it. If you take 1 electron from beryllium, you will be taking an electron from orbital that's fully occupied. So you will get 1s2 and 2s1. Only 1 electron. Well, boron, it will be 1s2, 2s2. Last orbital is fully occupied. Size of boron is smaller than beryllium. To the right side of periodic table, size getting smaller. Expected trend for ionization energy is that boron will have higher ionization energy than beryllium. But when you look to the last orbital, beryllium is 2s2, fully occupied orbital. This one is 1 electron, only 1 electron. And when I take 1 electron from it, I get this. I get fully occupied orbital. That's going to give you a stabilization energy. Taking electron from 2s2 will give you half occupied orbital. That's going to cost you more energy. So because of the orbital that we will generate after taking electron, we can see that in B, by taking electron from 2p, we get fully occupied 2s orbital, and that's going to give us some stabilization. And in reality, ionization energy of boron, it will be less than ionization energy of beryllium. Because beryllium, you are taking electron from fully occupied orbital. Again, there is a huge drop with the ionization energy because we switch to N3 and we go up, same trend there, and we get to argon. Now N4, another drop. In this area, ionization energy is almost flat. Reason for it, because we are dealing with transition metal, and with the transition metal, we said the size is almost same. If the size is not changing, then ionization energy is not going to change. And after that one, you go with, you will be dealing with the, 4p orbital. And as you move to the right side of the periodic table, size it will get smaller, so ionization energy is going to go up. Okay. Look to the lowest ionization energy in each period. The lowest ionization energy belongs to the, element of group 1. Group 1. So group 1 has the lowest ionization energy, and the highest one belongs to noble gases. Noble gases are the smallest element in each period. The smallest element in each period. Neon is the smallest element in N2, and lithium is the biggest element in that period. From left to the right, ionization energy is getting higher because size is getting smaller. Okay, so I talked about this one. I said nitrogen versus oxygen, because you are taking the electron from half occupied orbital, you will be spending more energy, you will be fighting with symmetry, while oxygen, you take electron from orbital that is not symmetrical, you will generate orbital that is half occupied. It has some symmetry, so it will pay off some of the energy that you spend to take first electron from oxygen. That means ionization energy of oxygen will be less than nitrogen, and as you see is 100 kilojoule, around 100 kilojoule is less than nitrogen. Here, first ionization energy for Mg, it says number is 700, the second double of the first one, 1400, but the third one is way bigger than the second or the first one. So I'm going to say that there is a jump, and jump happened here. So I will say cross this one. I see 1, 2. That means I have 2 valence electrons, and this ionization energy belongs to core electron. Core electron. So anytime you touch core electron, ionization energy is going to be huge number, because you will be dealing with electron that is close to the nucleus. And that's the reason, we say do not get close, do not get exposed to X-ray. Because the way we generate X-ray or gamma ray, we generate them by manipulating or, kicking core electrons. And when we kick those core electrons, there will be huge, exchange of energy. And that energy, it will have a short wavelength or high frequency, and it will be close to X-ray or gamma ray. And that one, that amount of energy, it can diffuse in your body, and it can mess with, some proteins or some bonds that we have in our body, like, DNA. Look to this bar. I see first ionization energy for sodium is 500 kilojoule. The second one is 10 times of it. So I'm going to say there's a huge jump, by switching from first to second ionization energy. That means we have only one valence electron, and this is belong to core electron. While for Mg or magnesium, we took first electron 700, second 1400, the third one now is almost 8,000. So I'm gonna say I have only 2 valence electrons, and the third one is core electron. For aluminum, first ionization 600 or 580, 1800, and third one is almost 3,000. Okay, so yeah, we see trend. We see that energy, ionization energy is going up. That's logical. We took the first electron from neutral. Now we are taking electron from aluminum +1. You're taking electron from aluminum +2 to generate this one. But then you will be taking electron in here. For the fourth one, we are dealing with aluminum +3. Okay, you take electron from aluminum +3, that means you will be dealing with core electrons. So why this one is a huge number? Because aluminum is 1s2, 2s2, 2p6, 3s2, and 3p1. So first electron it will be from p orbital. This is gonna be the first electron we will target. Okay, and it's causing charging us 580 kilojoule per mole. The second ionization energy, it will be from 3s orbital. Third ionization energy, it will be again from 3s orbital. So we can take 3 valence electrons. But the fourth one, you will be done with the valence electrons. There is nothing left for the valence electron. You will be taking electron from p orbital, one of these 6 electrons. This is the fourth ionization energy. And because it's a core electron, it will cost you more energy to take that electron. Okay, so now that I'm done with the trend for ionization energy, I will switch to electron affinity, and I will be talking about electron affinity. And let's see, what's the electron affinity? Okay, so the electron affinity is the energy that we will get, not spend. Okay, we will get this time to it's going to be a amount of energy that we will get whenever we give 1 electron to a species in a gas phase. Okay, so we're giving 1 electron to a species in a gas phase, and that's going to be electron affinity. Is negative, not positive. Because it's negative, that means the system is getting more stable. And because it's getting more stable, it will release or it will emit energy. And that's the reason you see is negative. Okay. Is negative. That means there is emission. Okay, or we are emitting energy. Okay. For ionization energy, we are spending. But in this case, we are generating energy. So I'm going to add the energy to the right side, not the left side, which is a reactant. So I'm adding to the product. That means we generated energy. Okay, let's see the trend for ionization energy. Electron affinity. Electron affinity is an exothermic process. Okay. Electron affinity generally to the right side is getting more negative. Down in one group is getting more positive. So electron affinity to the right side increases, and one group down decreases. So it's similar to trend of size. For size, we said to the right side. Sorry, similar to actually ionization energy. Ionization energy to the right side increases, down decreases. Okay. So it's the opposite of size, but exactly same trend, same or like, you know, ionization energy. Okay. Here, as we go to the right side of periodic table, ionization electron affinity goes up. We start with -60, and so here you see it says -27, and then 122, 141, and that one is again getting bigger. Then we reach 0. I will talk about those zeros. Why do we get 0? Okay. So to the right side, electron affinity increases, down decreases. And check this one: 73, 60, 53, 48, 47. So when we go down, we see decreases in electron affinity. Okay. Trend in electron affinity is not much solid like, you know, ionization energy or you know, size. You will see too many violations or deviations, you know, in with the electron affinity. And as you see here is 0, nitrogen 0, and last one is 0. Now let's talk about those zeros. Why do we get zeros? For beryllium, we have 1s2, 2s2. Last orbital is full. You want to give it one electron, you have to add the electron to p orbital. We are adding electron to the new orbital, and this is going to cost us, you know, it's going to cost us some energy. It's going to say, you know what, you generated one orbital that is neither half occupied nor fully occupied. Why do you want to get that electron? So there is less, or maybe not, you know, not actual will for getting new electron, and that's a reason, you know, you see it is 0. Now when it comes to nitrogen, nitrogen is 1s2, 2s2, 2p3. Last orbital is half occupied. If you want to add electron, you will adding electron to this orbital, one of this. So n plus minus 1 and minus 1, it will be 1s2, 2s2, 2p, 3 plus 1, 4. So we're going to ruin the symmetry that we have. The nitrogen is going to say, you know what, I have an orbital that is half occupied, there is symmetry in it, and you want to give me one electron, I'm going to lose the symmetry. Because I'm going to lose the symmetry, I don't want that electron. So it will resist against, you know, accepting new electron. And as you see, electron affinity drop down to close to 0. Okay. Now you move to the right side. Again, ionization energy is going up until you reach the noble gases. Noble gases they have last orbital that is full. If you want to give electron to neon, you have to put it in a 3s orbital, and this is n equal 3. That means you are dealing with element from this period. Well, neon belongs to the second period. Why do you want to give me one electron and and force me to put it in a higher layer of energy? I don't want to do it. It says I'm full, so I'm not going to accept any electron. Okay. And when we go down in one group, again, the electron affinity decreases. But check this group 7. When we go down, electron affinity from fluorine to chlorine, we see jump actually, and increases, and then decreases. What's the story about those two? Okay, fluorine is so small that when you give it one electron, a new electron, it will see the rest, and it will have repulsion with them. Okay, so let's write it somewhere. We have fluorine, that 1s2, 2s2, 2p5. Here fluorine. Okay. First layer in 1, we have 2 electrons. Second layer, we have 7. Three. Okay. If you add one electron, a new electron, so anything that we are adding, it will see 7 electrons, 7 there, and size is really small. So it will have repulsion with all these electrons. And you will see too much repulsion. Because of the size of fluorine is so small, you will have too much repulsion. That repulsion, it will make the system unstable. So fluorine is going to say, you know what, because of the repulsion that I'm going to get, I'm not much willing, to take electron. But still, the will is way higher than many elements around fluorine. When you compare it with chlorine is way bigger than fluorine. Chlorine, it will be this is chlorine. First layer, second layer, third layer. Third layer, again, you have 7 electrons. Okay, 5, 6, 7, and you are adding electron to the to the last layer. Okay. Look at the distance between electrons and compare it with fluorine. Distance between the electrons when it comes to chlorine is way bigger. Okay, because of the size of the element. So they're going to say, you know what, we can kind of move around and make a space for the new electron. We can put it somewhere between us, and we're not going to build too much repulsion. We have enough space. So because of the size, the new electron is not going to generate a huge amount of repulsion. And because the system is not building too much repulsion, it will have more will for getting electron. Okay. Now the question is, why do we want to get electron? We want to get electron to be like noble gases. We want to get electron to make the last orbital fully occupied. If we make it fully occupied or half occupied, we will get some stabilization. System, it will be stable. That's the reason oxygen is trying to get 2 electrons, because if you give it 2 electrons, it will be like neon. Sulfur try to get 2 electrons to be like argon. Okay. And so When it comes to oxygen, we say O is -2. For fluorine we say F -1. Because if you give it 1 electron, it will be neon. Oxygen, you give it 2 electrons, it will be neon, and they will be really stable. So that's the reason always we say group 7 -1, group 2, group oxygen is -2. And for nitrogen, if you give it 3 electrons, it will be equal to neon. Okay. And last discussion from this chapter is going to be the electron affinity. What's the electron affinity? Is the trend, not like we can put it this way. Metallic character is, as you know, like when we talk about metal, we say metals tend to conduct electricity. So metal will form a cation. And when we talk about metallic character, we want to know how much that element is capable of making cation. Is it ready to lose the electron? If it's more ready to lose the electron, then we say that metallic character is so high in that element. And here, metallic character will follow a size trend. Okay? Metallic character will follow the size trend. So group 1 has the biggest size in any period. And when we move to the right side of periodic table, size decreases. Because size decreases, less electron will be closer to the nucleus, so that element will not be ready to lose the electron. So we say the metallic character decreases. And as you see, metallic character decreases as we move to the right side of periodic table. So here, left side is the area that we accommodate metal in it. So I say this one is metallic. I'm not talking about the transition metal. Here, we're talking about transition metal. Then you will have, the radioactive metal, the lanthanide and actinide metal, elements here. And this one also is metal, aluminum is metallic. But then you will be dealing with non-metal, like phosphorus, sulfur, chlorines. So as we move to the right side of the periodic table, size decreases. Because size decreases, we say the metallic character decreases, and we will have mainly non-metal. But as we move down in one group, metallic character increases. Because size is getting so big, you don't have much control to the last electron, and you are more, you are kind of ready, and you are capable of losing that electron. Okay, but check this one. Let's check a group, for example, group 15 or 5. Nitrogen is non-metal. Phosphorus, it still is non-metal, but we use phosphorus for semiconductor. Arsenic, yeah, same thing. And as you move down, then you will be dealing with actual metals. Lead is somewhere here. You start with carbon, silicon. Carbon is non-metal. Silicon, we use it as a semiconductor. And as we move down, we will reach lead. We know lead for sure is metal. Okay. So as you go down, size increases. That element start to behave like metal. And as you see here, nitrogen, phosphorus, arsenic, and then until you reach the bismuth or Bi, you see this one behave exactly like metal. Even the group is a non-metal group. Okay, So the trend for metallic character, similar to the trend of size, as we move to the right side of the periodic table, metallic character decreases. To the right side, metallic character decreases, and as we go down in one group, metallic character increases. Okay, metallic character increases. Why? Because when we move down in one group, ionization energy goes down. That the last element, last electron is way far from the nucleus. You don't need to spend too much energy to take it. With small amount of energy, you can take it. So ionization energy, it will be less. Because it's less, we say that element behave like metal, is capable of losing electron, is capable of forming cation. So the metallic character, it will be higher. Okay, I'm gonna start the lecture here, and I will share this one with you. And I hope this lecture was useful. Have a great time, guys.